but I'd like to thank SAICE for the opportunity to share this project with us. We've very much enjoyed working on it, and we hope that you'll benefit from it. Just busy sharing our presentation.
All good, Pierre, you're good to go?
Great. So I'd also like to, apart from thanking our host, SAICE, I'd like to thank our client, the Wykeham Collegiate Independent School for Girls, TWC, for being such a great client on this job. They gave us so much helpful input, but they also were flexible enough, allowing us to be creative. And I'm sure you'll agree that the finished product attests to them. So firstly, I just want to say that this is for educational purposes only. Might be obvious, but you know, if you take on board something from what we say and it doesn't go so well on your own project, please don't hold us liable for it. Okay. Yeah. So just we're going to have a few short presentations. The current one is the introduction, and I would like just a single slide to talk about HN Consulting Engineers, if that's okay. Just for those who are interested in partnering with us in the future, and then we'll get onto the project. Then after that, Jimmy's got to get into the meat of it, the structural and civil design, and Mdeni is going to do the electrical design. And then I'll wrap up with construction, and then a walkthrough of the finished product. We'll end with 2 videos. Please stay to the end. I'm sure you'll find them fruitful. And we'll take questions after the structural and civil design, after the electrical design, and then after my final session. But if you don't get to ask any questions, my email address is at the bottom, pierre@hn.co.za. So this is that one slide about HN Consulting Engineers. Our head office is in Maritzburg. These are some of the projects we've worked on in the last 22 years. We're a member of Consulting Engineers South Africa. We have an ISO 9001 certified quality management system, and we're level 1 BBBEE. And we offer various services, right from, as you can see, roads, bridges, water, sanitation, and buildings, including renovations and new buildings. The one that you see in the bottom center is a conceptual design. It's not yet built. So the SANROL Eastern Region offices, the new SANROL Eastern Region offices that are going to be constructed in Hayfields, Pietermaritzburg. And we're already in discussion with SAICE about presenting about that when it's at a more advanced stage. Someone's just posted a comment that the slides are not showing, but I know some others.
Now, they are showing on our side. I think if that person can log out and log back in, you are still on slide 3 of 8. Yeah. We can see them. Thanks, Pierre.
Okay. So why did we need this bridge to begin with? That's always the question you've got to ask at the start. So the Wykeham Collegiate is a private girls' school in Pietermaritzburg. It's from grade RR through to grade 12. The main campus is shown here. It's in top of Clarendon. And there's a public road, Villiers Drive, that separates their main campus from their additional properties. And so, as you can imagine, the girls are having to cross this road. It's a very busy road at times during the day. And that raises all sorts of risks. There's the risk of traffic accidents, but there's also stranger danger, and various other risks like that. There's also a need to constantly control accesses to the property and to the various properties. So it just makes sense to keep them all on the property. And so you build a private bridge across from one property into the others across the road. So that was the rationale, and that's the rationale on the basis that they approached us wanting a bridge. And what's more, you can monitor traffic on the bridge. They've got CCTV cameras that are being installed. So it's much easier to control access to the properties as well as to monitor traffic moving between the properties. So that's the why. And then the main role players, of course, you've got TWC, the employer. You've got the designer and engineer being HN Consulting. The main contractor, Ingonyam and Nikon, a grade 7 CIDB. And the subcontractors, the main subcontractors were Steelcon Projects, CM Engineering. So Steelcon was doing the major steel work like the deck. CM Engineering, they were more involved on the balustrades for the stairs. And then electrotechnical agencies, the electrical contractor responsible for the lighting. I must admit, this team of contractors did, in my view, a very good job with the finished product. So I'd like to commend them for work well done on a technically challenging project. So the construction had started mid-January and it's finishing about now. We are in fact opening the bridge on Monday. Total investment, including consultant fees and construction, came to 5.3 million rand. For the form of contract was the GCC, General Conditions of Contract 2015, and the project specs is COTO 2020, which is being quite commonly used at the moment. And we invited 5 specialist contractors. This is definitely a specialized job. And so we had a closed invitation of among the best contractors in the country. And Ingonyama Nikon were the ones who were successful. Along the way, we had the pleasure of promoting science and engineering to high schoolers. So on the left, we've got the Wykeham Collegiate's grade 11 and 12 science students. And then on the right, we've got boys from Maritzburg College on work experience. We were very impressed with their level of participation and the quality of the questions that they asked. Okay, so that's the end of my introduction. I'm going to hand over to Jimmy to start us with the meat.
You look a lot grayer than your picture in the advert, Pierre. I'm not sure if you found one from an old wallet of long ago, but either that or this project has aged you. So,
yeah, probably. It's about 3 years out of date, I have to admit.
No,
my wife says I'm improving with age.
Yeah, well, then that's all that counts, Pierre. Like a good red wine.
Hi, everybody. I'm presenting the structural and civil design. I was the design engineer on this project. Okay, my presentation overview. First, I'll go over the project terms of reference, and then I'll go over the design options that we considered. Then I'll also present the preliminary designs that we came up with, and then the final design option I will also present it, and I'll go through like the drawings, the design and analysis, and the fabrication drawings. Okay, the terms of reference. The scope of works that were undertaken by the contractor, we opted for site option 2, was to construct a pedestrian bridge over the Villiers Drive across the car park. So the various work items were relocation of existing services, power and telecommunications, foundation excavations, decommissioning of existing infrastructure. Then the foundation, stairs, columns and piers are structural, landings and decking, bridge frame and hand railing structural. Then we had lighting, and then also a bit of landscaping and finishing, which is civil. Then to undertake the work, we also employed various sub-consultants, specialist service providers. We had a survey, a topographical survey undertaken. And then we also had to undertake a geotechnical investigation to understand what the soil properties were and to help us design the foundations. And then we also consulted with an OHS consultant, and who's had input from inception. And I know it doesn't say anything here, but we did do an environmental screening as well. So there was no environmental triggers for this project. Then we had quite a lot of service owner engagement before we could start the project. With the Msunduzi municipality, we had to consult with their electrical section, roads and stormwater, and their building sections. And then we had to submit applications for wayleaves, for relocations of services, and also plans approvals. And then telecommunications as well. We also had to relocate services as well as electrical. Okay, I'll get on to the next part of it. At concept stage, we considered various different types of bridges that we thought would, suit this project, and we kind of had a look at different bridges around, and from what we see when we're driving along, and also from going on the internet, and there are various standard types of bridges. So a cable stay bridge we considered, but I think the span is a little too small for it to warrant that design. But this is the bridge that's at the Marinial Toll Plaza in Durban, and the span is 95 meters. Another type of arch bridge we kind of considered was also an arch bridge, and also we kind of thought the span would be a bit small for that to warrant this construction. This bridge here is the Humber Bay Bridge in Ontario, Canada, and the span's 115 meters. Then I kind of thought, no, probably a steel truss bridge would suit, because we can't do a concrete bridge because we'd have to have all the formwork and everything. And if we were to use precast beams, 30 meters is a bit of a stretch. So we considered using a steel bridge with I sections. I thought a bridge that would kind of suit our design is this bridge that's in Ladysmith, that crosses over the N11. The span's about 23 meters. So our conceptual designs were kind of based on this concept. And then another bridge that we came across as well from searching on the internet is this bridge in Johannesburg, which crosses over. It's Jeppes Girls High School Bridge in Johannesburg. Spans about 38 meters. So between those two options, we kind of thought that that would be the best solution. So at prelim design stage, we start. First of all, the client had two potential sites where they wanted to put the bridge. First was further up the road. The bridge span would have been 22 meters. So we considered the two options. So we prepared some renders to present to the client. So this is like the plan view of it that would, if it had been constructed, and then this is like a 3D render that we did to present to them, which is very similar to that bridge in Ladysmith. Then the other site is lower down, goes across their car park, and this is actually the site that they settled on. The span is 32 meters. So I was still working with that initial concept. I just made it wider And this was the original prelim design that we presented to the client. And then they kind of thought, no, the Jeppe Bridge looks kind of nice as well. Why don't we go for that sort of design? So we tweaked this a bit so that the radii of the top chord and the bottom chord are 3 meters apart, so it's a constant profile across. And then this is the final concept that we presented, and that this is what they settled on. So this was a 3D render that we produced of the design that they accepted, and also they wanted to have clear view fencing on the side of the bridge instead of handrails. So we also adopted clear view fencing as well. So so that's the design that we continue to tender with, and then I can quickly run through the construction drawing. So this is the plan view of the drawing of the bridge. And then I can show you the elevation. This is the elevation of the bridge, and then I can show you the cross section through the bridge. You can see on that section that there's a line there, which is it's a clearance diagram above the road, and it has to be at least 5.2 meters, which is the standard clearance that you require on bridges. So so that clearance diagram kind of dictated the height of the bridge and the piers. The span of the bridge is 32.4 meters from pier to pier, center of pier, or you could call it bearing to bearing, 32.4 meters. And then there's a cross section through the bridge, and also like a 3D view of the pier and the stairs. We went for a spiral staircase. The bridge width is 2 meters, which is a standard pedestrian bridge width. And then, now I'm going to run through all the design codes and standards that we use to design this bridge. So the loading and safety factors, we complied with TMH7. We applied serviceability and ultimate limit state principles. It includes considerations for dead load, live load, wind actions, vibration, and thermal loading. Concrete, we designed as per SANS 10100 with specific properties for different structural elements, ensuring durability and strength. Concrete grade was 30 MPa. Reinforcing, we used high tensile reinforcement grade. Reinforcing grade is 450 MPa. Structural steel, we designed according to SANS 10162, and the structural steel grade is S355JR. Then foundations are designed in accordance with SANS 10161 in consideration of the geotechnical investigations that indicated the presence of silty clay with a low bearing capacity across the site. So in designing the bridge, I used Revit. So I used Revit to create a model, brought in the survey data and everything, and modeled the bridge in Revit. And from Revit, if anyone's familiar with Revit, you basically model the structure or the building or whatever you're doing, and from that model you can generate all your sections, elevations, and etc., and also your detailing. So also did the structural steel detailing and the reinforcement detailing in Revit as well, and produced all the construction drawings for the contractor. And then as the contract was progressing, the steel contractor wanted us to send them the BIM model, so we sent them IFC file of our Revit model, and they used that in Tekla structures to generate all their fabrication drawings. And they've sent us back their BIM model, their IFC file, along with all their fabrication drawings for approval. So it was quite a seamless process. Then the next part of it is, the structural analysis, which goes hand in hand with the modeling in Revit. So for the structural analysis and verification, I use Robot, which links to Revit. It's also an Autodesk package, and then from that I could generate my model, and then plow the loadings, and then calculate the sizing of the members that's safe and economical, that passes the the design codes. So from all that, we sized all the members, and then in the Revit model, we just changed the size of the model of the members to suit what we actually designed. Okay, then I can just run through all the the design data and the results of all the analyses. So our design span is 32.4 meters. The mass of the steelwork girder is 10.9 tons. The concrete deck is 25.2 tons. So the dead weight of the structure works out to 10.93 kilonewton per linear meter. The live loading from TMH7, the pedestrian load from clause 2.7, worked out to 8.78 kilonewton per meter. Then, after having done all the analysis, we determined all the the deflection from the dead load was 16.3 meters. And then the deflection under live load, dead load, and live loading, the ultimate deflection was 30.1 millimeters, which is very low. Then we also needed to know what the horizontal deflection would be at the bearing. So under dead loading, it's 5.4, and then the ultimate movement is 10.1 millimeters. The bearings have got 50 millimeter allowance, but it's plus or minus 25 millimeters either direction. Then we also needed to do vibration analysis on the structure, and so for that we need to do a modal analysis in Robot, and from that I was able to determine that the natural frequency is 4.46 hertz. But for people walking, the frequency is 1 to 2.6 hertz. So there shouldn't be any risk of the structure also resonating with people walking over it. Because I'm sure you've heard of bridges vibrating when people are walking on it. A famous example is the one in London, the Millennium Bridge, and they had to close it. At the opening ceremony, people were walking across the bridge and it was resonating, and yeah. So yeah, we've considered that. And then as a check, in TMH7 clause 2 C.1, the allowable vertical acceleration is 1.06 meters per second squared, and then our calculation, the maximum would be 0.54 meters per second squared. So it's compliant with respect to that. Then the final thing I want to just explain is also the design of the foundations. So the foundations, the allowable bearing pressure that the geotech report indicated 60 kPa to 100 kPa. So under the dead weight of the structure, it's sitting at 60 kPa. Then a transient load, if it's ever fully loaded, it would go up to 100 kPa. So that yielded a foundation size of 6 by 6 meters, which gives us an area of 336 meters squared. Okay, that's most of my presentation, but I'm just going to go to the last slide and I just want to share with you my favorite expression. Any idiot can build a bridge that stands, but it takes an engineer to build a bridge that barely stands. Thank you. Okay, are there any questions?
Jimmy, there are a few things in the chat. I don't know if Pierre's been monitoring the chat as well. Let me just go into those for you. Besides people having difficulty seeing the slides, but it's all working fine on my side. I'm assuming it's their systems. Now I've got to find it in amongst all these AI bots that pop up.
I can see the chat, yeah. Okay.
Okay, so the question from Leon, maybe you or Pierre or you collectively can ask, why a topographical survey? What was the significance of it? I understand the geographical one. What does the topographical one do except offer elevations?
Okay. Yeah, well, basically, you know where we took the long section of the bridge. So we need to also know what the profile of the natural ground is. And then, you know, so we can also, to give the contractor levels for the whole project, there's levels for it has to be a level on everything. So design level for all the components. So also the surveyor gives you benchmarks. So the contractor, when he sets out the bridge, he sets it out using the surveyor's benchmarks. So we make sure that the bridge is in the exact position that it should be, and also like we give them coordinates of all the points on the bridge, like this, you know, the center of pier and edge of foundation, stuff like that. So it's easy for them to set out. So the survey is it's a very important part of the design.
Hey, there's another one here, Jimmy. It's which program, software, in other words, did you use to create your preliminary renders?
Okay, I use Revit for that as well. So Revit, you can do rendering, and you can actually brought in back like a picture from in the background, and you know place the bridge in where it would be in real life, and created a render doing that. Yeah.
Okay, then another one, and you mentioned you went for a spiral staircase. The question is, does TWC have disabled students in the school, and did you consider it when designing the bridge?
Yeah, I did mention it to them, but you know, the cost of ramps and things, you know, the ramp has to be at 1 in 12. You know, yeah, I think they may look at it in the future, but it isn't part of the project now. But Jimmy, I have mentioned it to them.
Yeah, knowing the sites, your other problem is a 1 in 12 to get to a height of, what was it, about 5.8 at where the staircase joins.
It's about 5 meters.
Okay, so you'd have to have a ramp that would sort of start down at the.
It'd be 60 meters long, yeah.
Yeah, that's the next challenge. So you start up at one of the boarding houses, and anyway. Okay, so and then I think you did mention this in one of your slides, the standards that you used in terms of the design, the SAN standards. TMH, you mentioned one of the TMHs.
Yeah, TMH7, yeah.
Okay, is that
the design loads? Yeah.
Okay, specifically for bridges or for pedestrian bridges?
No, TMH7's got for bridges, but it's also got a section for pedestrian bridges as well.
Okay.
So it's a part of TMH7. It's got a design loading for pedestrian bridges.
Yeah.
So it's actually 5 kilonewtons per square meter for a bridge up to 25 meters, and then past 25 meters, it's 25 divided by the square root of the span.
Okay. Ish, now you're getting too technical. There was a question here that did you calculate for wind loading? I think you did mention it, that it was one of the considerations.
Yeah, I did work out or determine what the wind loads were, but they're negligible compared to the pedestrian loading. So they're not the critical load case.
And then this question, I'm not sure I even understand it, but I'll try you. How was the camber in the steel decided upon? I'm assuming he meant the curve in the deck.
Oh, the curve, yeah. Just for, I think, for an aesthetic aspect, eh?
Okay, and then the next question is
for the way it looked, yeah.
Yeah, so it's like a curved version of that Joburg school, which was a flatter deck. I think if I remember.
No, theirs was also more. I think their camber is actually more than ours.
Okay.
Yeah.
Okay, then the question was, now I've lost it. Did you use circular members? You've not gone into the detail. Circular hollow sections.
Correct, yeah.
Okay, and then
Stacey, lots of questions here, right?
Hey, there's lots of interest. Yeah. This is worse than a peer review check here.
Okay, what bearings were used? We used they're called Honel, the Honel bearings. Honel. They've got Teflon in them, and they're metallic, and they slide. I think they're called C bearings.
Okay.
And then you
there's-
get different fixities bearings. So there's a bearing that can move in all the directions, and there's one bearing that's constrained in one direction, and it's got the 50mm movement on the one. So those are the ones that we used. Yeah. Okay.
Are you looking at the questions there, Jimmy? So
I
don't
can
need
see
to
the
look.
questions. Yeah.
Okay, cool.
So
you look at them,
interesting
and I'll just check their
presentation.
hands.
Thank you. I wanted to ask if the modeling software used during detailing design match with SAICE design codes. Yes. Sorry. Yeah, this robot has got South African design codes in it as well. It's got the South African steel code in it. Okay, can you please touch base on the stormwater part on bridge structure? Well, yeah, the bridge has got that camber, so we didn't really worry about it because we don't have weep holes or anything. Okay, what type of foundation did you end up with your design with the load bearing of 600 kPas? No, no, it's 30 kPa, it's 100 kPa and 60 kPa. That's bearing capacity. Which standard is applicable to determining the pedestrian bridge width? Okay, that's a DOT standard. There's a DOT standard bridge cross section. It has to be 2 meters wide. Was the frequency derived from the software exactly the same as that calculated using TMH7? Okay, TMH7 was written before they had very advanced software. So they do have methods to calculate the natural frequency, but the software can calculate it. So we used the TMH, the natural frequency calculated from the software, and then I put it into their formula. Okay, given the clay soil, were spread footing sufficient or micropiles considered? Yes, so spread footing was sufficient because the geotech engineer gave us the potential settlements, and it was within the allowable. So that's why we opted for that. If we had gone for piling, it would have been a lot more expensive. Okay, what type of bridge bearing did you use? Fixed pinned. Okay. All right. So for the bearings, one side is fixed and the other side is free. It's like a roller. May you mention the software that you use, not Revit, the other one. Oh, it's called Robot Structural Analysis. It's also from Autodesk. So it comes in the AEC collection, which is a package of software that you rent every year from Autodesk. How
Jimmy,
much
Jimmy, I think it's the Autodesk version of Procon.
Correct, yeah, it is. You know, we have Procon, but it's so expensive, and we realized that we get this robot with our AEC collection, so we kind of have done away with most of Procon. We're just using robot now. Okay, did you generate bending schedules from Revit? Yes, and it does have the South African shape codes. Okay, hi Jimmy. On foundation designs, how did you calculate the size of holding down bolts and base plate? What allowance and tolerance did you come up with? All right. So yeah, the bridge is on bearings, so it doesn't really have holding down bolts, but one side is fixed, and then everything else is concrete. So there's not really any holding down bolts. And then the bridge itself is pretty much all those members are welded together, and except for the bracing at the top, which was bolted on site. I think we've gone through all the questions.
Okay, Jimmy, there was a hand from Malasedi. I've enabled you to unmute if you want to ask your question to Jimmy. Malasedi,
hello everyone.
There we go. There we go.
Malasedi here. The question, I have few questions to ask. I'm a civil engineer, like a student myself. So in the past, we have been like encountering failures within our industries, especially bridges collapsing, bridges not being completed. So how do we mitigate such things from happening? And as yourself as an engineer, have you ever experienced or witnessed any significant structural failures in your project? And then if yes, please can you like describe? And then what were the primary cause for these failures? Like were they like designer issues, errors, or material defects, or
yeah, look,
it can be anything, right? So
we
how do we
as engineers, we design things to design codes which specify the the loading that we require, and then we have to as make sure that what we're designing is safe. We have to calculate all the forces and stresses and make sure that it complies with the design codes. And yeah, I've never had any structural failures of stuff that I've done. But yeah, I think it's negligence when it happens. Maybe the engineers that design things don't design it properly. Also, I think a big gap is the supervision on site. So, an engineer will design reinforcing and stuff, but if he doesn't check that reinforcing is put into the concrete and it collapses, that could be. I think that's also a primary issue that causes failures is lack of construction supervision.
Okay. After that, like, do we have emerging trends or technologies like that you think will increase the risk of failures in our project, or how do we like address those failures because they continue happening? Like it's a lot happening like right
now. Yeah, I know.
So.
Look, we as professionals, like we're very interested in like for instance that collapse in George. We'd like when that report comes out, we'd like to know what caused it, so we know in future, what mistakes not to make. So yeah, it's a high risk. It's a very risky thing that we do, but we have to have our due diligence in our work and make sure that what we design is economical and safe.
Yeah, Jimmy, maybe just another observation. Everybody will remember the Greyston Pedestrian Bridge collapse.
Yeah.
But I think if you Google Greyston Bridge collapse and get the final report, you'll find that it was probably more as a result of leaving stuff out and not doing the temporary works properly.
Yeah, so your decision that was the problem there.
Yeah, exactly. Your decision to go for a craned in steel structure and not put in, because of constraints, temporary works actually reduces some of the risk attached to. So yes, it would have been occupation of road reserve and various other constraints with formwork, but the contractor is responsible for the temporary works, and they don't often bring in the PR rangers like Jimmy to check their temporary work. So that's one of the challenges. But EXA, Bridget Samula has asked the SAICE structural division to collaborate with EXA, because EXA as the regulator is actually very worried about the fact that the majority of failures, besides the odd slimes dam and things like that have failed, relates to a structure of some or other kind. So I think it's an educational thing. And as Jimmy says, if you don't have a value system and stick to the EXA code of conduct, then you will start to have problems. But fortunately for us, HNN, I think half of them are my students. They won't do anything they shouldn't do, except for Jimmy. Jimmy, are we going to move on? Otherwise, you'll be all night talking.
Yeah. Okay, I'm gonna hand over to Pierre, and then Pierre can hand over to Mdeni. Thanks.
Thanks, Jimmy. We're just going to bring up the next presentation, and our colleague Mdeni Shange is going to take over. He's an professional electrical technologist, and he's going to focus on the electrical side of this. Now, you might be wondering why in a civil engineering presentation we have an electrical side. Well, my brother-in-law needs his full CPD points, so we have to fill up the 1.5 hours. Just jokes aside, it's important that we have an appreciation and understanding of various other disciplines. as professionals, as part of a multidisciplinary team, we need to know when to engage other specialists and have due respect and cognizance of their expertise. So let me hand over to Ndeni.
Good evening, everyone. My name is Ndeni Shange. I work for HN Consulting Engineers. I'm a senior engineering technologist specializing in electrical engineering design and project management. I'll take you through the design. Okay, the scope of works for the electrical was for Msunduzi and the telecom relocation of services, the low voltage underground reticulation system, the CCTV, the CCTV and the kiosk A distribution system, the student boarding residential standby generator installation system, bridge lighting, lightning protection, and the lighting. So I'll start with the overview that in the beginning we had an overhead line, as you can see from Umsunduzi, which is the supply authority. That overhead line needed to be disconnected and converted into an underground system. And then across the road, we had an overhead line, which was for telecom open services, which that also needed to be relocated into an underground system. An application was logged, and when that application was logged with the drawings that were accompanied, the electrical overhead lines were disconnected, as you can see from the drawings, and they decided to terminate a new underground cable, which is a 300 mil 3-core aluminium, which then connected to the other side of the road and then serving to provide service connections to the households and the sports fields, the musical area for the TWC, including other houses as well. With Telkom as well, they were able to do an underground conversion, and that has been done successfully. As you can see from the conversion, this is the top section of it. So what they've done is disconnected the overhead line and kept the overhead line, which is crossing, which is feeding the student boarding housing for TWC. On the bottom section of it, that's where the underground cable was installed, which is a new one which crossed the road. And that was a 300 mil 3-core aluminium, which was used to terminate into another overhead line across the road, serving as a main supply to the households on that area. Then the detailed design, this is the detailed design overview. So the detailed design overview of this project was to provide bridge lighting, bridge lightning protection, an underground system which will be fed from an existing sports field center on the main campus, where I've done the load logging and did a load analysis to determine whether they have sufficient capacity on the standby generator in order to provide the underground systems which will cross the bridge and then feed the student housing as the recommendation from the client. So as you can see from the right-hand side, you've got there the sports field center, which is a DB LHC. That is the standby generator distribution board where I fed my supply from. And then I've reticulated just next to the open area on the sports field, heading directly to the distribution kiosk, which is on the bridge, which I'll show you on the next slide. Types of cables that I've used, I've specified 95 mil 4-core from DBLHC, heading directly to kiosk A on the bridge. That was reticulated within the 110 mils diameter PVC flexible sleeves. So when it comes to the distribution kiosks, I've done all my calculations. That is for the bridge lighting, the CCTV, which obviously was going to be done internally, but I had been provided with all the load that was required for the distribution kiosk, and also did an analysis on the student boarding house distribution board, which carried 100 amp three-phase. Then in addition, recommendations that we require from the CCTV was to have a CCTV kiosk, which will be independent. That is obviously done by a specialist, which was going to be obviously included as an external scope of works, but I provided all the power supply that is required for the CCTV, which is not much power because it just needed a 6 mil 2-core supply cable, required a small distribution boards, standard normal surface mounted plugs, which are bearing a SANS 164-1 code. The distribution kiosks for kiosk A and kiosk C are IP65 rated. And secondly, they are designed in the 3CR12 1.2 millimeter stainless steel, and then coated with electric orange color for the kiosk A and for the CCTV gray. Then on the student boarding side, there had to be a changeover panel that is required, which this had to be an external IP65 rated changeover panel. This is an automatic transfer switch. So the supply cable that is coming from the kiosk A, on the main campus side, you have a supply cable going over the bridge underneath the lining, which is clamped properly. And that's a 70 mil 4-core, which will be serving to supply a changeover switch. And then they have a municipal supply next to the fence line, which is connected to the changeover switch. So should they be load shedding, faults, load reduction, there's an automatic transfer switch that is able to do the changeover. And then the student boarding housing is able to continue functioning normally. Reticulation and lighting protection design. As you can see probably just a little bit of red underneath. That's where the supply cable of the 70 mil 4-core will be crossing underneath. What I've done in the main big column was to put 110 mil sleeves. And then for the lighting, I put PVC 25 mils, 3 by 25 mils PVC. And then for the lightning protection, I used 2 by 32 mils PVC sleeves. And then also made allowance for another 50 mil sleeve for the CCTV, which is going to be done by the specialist. But obviously I had to provide wireways for that installation to happen. The lightning protection here, soil resistivity was conducted and a soil resistivity report was received. And therefore the design that I'd recommended installing a 25 mil BEC lightning protection droppers connected to earth rods underground with bonding just at the low section of the bridge, because the bridge is all structured and interconnected. This system is very important, especially in Pietermaritzburg, based on too many lightning strikes that is usually occurring in these areas. And therefore, this type of design of providing lightning protection is very critical. This is the schematic diagram. As you can see, the main supply, I'd added an additional 125 amp 3-phase MCB, which is a circuit breaker, where the sports field existing distribution board is. With that, it was distributed with a 95mm fork hole into a kiosk, distribution kiosk A, which is mounted on the bridge. And from the bridge, I had allowed 100 amp three-phase, which will cross over to the student housing, and also allowed circuits for the bridge lighting and some spare capacity. Also, type 2 protection device was being used as surge arresters for each distribution kiosk. The second one is the CCTV, which also encompasses circuit breakers, 10 amps and 20 amps single phase as per requirement for the CCT equipment that will be installed. The bridge lighting elevations will actually just show you what I've done here. The best analysis when I went through in terms of what type of lighting will be required for an arcing bridge. I first considered linears, but linears usually are straight and obviously do not arc with the bridge, and therefore obviously have a bigger base luminous base for it, and it wouldn't have looked aesthetic. Despite even trying to get the minimum length of 660 millimeters, that wouldn't have worked aesthetically well. So I opted for a new design, which was divided into 9 sections. So if you're just looking at the bridge, it's got 9 sections. So that was divided into 9 sections, with each 9 section having 3.42 meters of a NeoCell IP66 luminaire with an opaque diffuser. These luminaires are very small, they're very aesthetic, but obviously what assisted with this is even the trunking is flexible, so that means it arcs with the bridge itself, making that much more pleasing in terms of aesthetic looks and also its operation as well. Then on the columns, I went for cubical up-down lights, which each column has 4 cubical up-down lights. Those cubical up-down lights are in different heights based on the spiral bridge, the spiral staircase that's heading down. So obviously in each area, we want to make sure that we are lighting up the entire staircase from the top to the bottom, accommodating lighting for movement at night, for students as well when they're heading back to their boarding houses, or if they're doing activities in across the road in the sports field or musical centers. Then this is just the top view of the lightning protection design, a distribution kiosk which is mounted on the landing bridge. It is an IP65 rated, but in order to give it a beautiful look, we created a cavity on the wall and then obviously mounted it with using bolts, 4 bolts on each corner. In order to make sure that the NeoCell 17 watt per meter luminaire that I'd chosen for the bridge, a simulation was conducted and the results were yielding very well. It's 126 lux that was required for this bridge based on the type of luminaire that has been chosen. The software that was used is Dilux, which obviously is for external lighting designs. So these are the equipments that I've used in terms of lighting the bridge. On your left, you can see that is the NeoCell with its trunking, which is gray in color, just like gray in color. It's a 17 watt per meter LED. I used the color temperature for 4000K for this light fitting. And then these light fittings obviously do not function at your normal 230 volts supply. They obviously will need a DC control driver, which you can see on your left, which steps down, which converts your 230 volts AC to your 24 volts DC control drivers. These control drivers are mounted inside this IP68 control drive box, which is able to house 2. So if you looked at each section of the bridge, you will have 2 control boxes with 2 control drivers based on the circuits and the calculations based on the required distance of the wiring itself. Then on your right-hand side, you've got the 17-watt LED cubicle up-down lights. Because these ones are very much close to the road other than the bridge, which is high up at above 5 meters. I've used the color temperature 3000K, which is obviously a warm white kind of color, which doesn't produce too much glare when the drivers are moving through. Then here, this is the completed version of the lighting design that I've done. This is on the spiral stairs. And then if you're looking at the side on your right-hand side, you can even see the cubicle up-down lights, not just providing lighting in the staircase itself, but also giving the bridge a nice, luminous, aesthetic look to it. This is the top section of the bridge. And as you can see on the left and the right-hand side, you've got the neo cells, which are 3.42 meters in length, which were cut. These were actually terminated in terms of the wiring. We used the arcing structure on the top because it's hollow. So all the wireways are hidden within the top hollow structure, and a looping circuit has been designed for this. And at the center of the bridge, you will find the control boxes with the drivers controlling these neo-cell LED lights. This is another view from the floor area, looking at how beautiful the bridge came out with the lighting, and it meets all the lux level requirements. This is just another depiction of the bridge lighting from a far view to just see the complete look for people that will be passing through. This is the type of scenery that we're seeing on the bridge. Thank you. And any questions?
Danny, if you can pop across to the chat, I see Masalasele has a hand up if you'd like to go ahead while you are looking for the chat questions.
Let me see. Okay.
There we are. There's one of the audience has a question first.
Okay, they can ask the question.
Masalasele, please go ahead. Okay, there. I think Rocky is also wanting to ask. Let me go ahead, Rocky. You can unmute.
Okay, good day, gentlemen and ladies. You have since indicated that provision of a standby generator was part of the scope of work. I just want to understand that did you connect the power supply to this newly installed light, or the generator was actually catering for the other buildings except the road crossing? Okay,
that's a good question. So basically, TWC are very, very well in advance with the electrical system. They have an existing, which is actually not, it is existing, but it's a new standby generator which has been installed last year. It carries a 500 kVA power, prime power. So it caters for the main campus, and it has a lot of spare capacity based on that. They were thinking of the future of connecting the emergency standby generator to the boarding housing across the road. So that was already been catered for. They even have a solar PV grid tied system as well as a backup system. So the generator was already existing. I had to do a load analysis and determine whether the 125 amp three-phase required for this project can be handled by the standby generator, which that yield well. Is there any other question?
Let's just get some from the chat for you. So there's a question from Spetlele. He says that, have you considered glow-in-the-dark concrete throughout your career, not necessarily only on this project, but with your linkage with HN in terms of them doing bridges and other things, considering we are experiencing electricity problems in our country?
They mentioned about glow in the dark. Did they mention just glow in the dark?
Glow in the dark concrete, luminous concrete.
Concrete.
Yep.
Maybe I don't think that relates to the electrical engineering side. Glow in the dark concrete. I mean, I'm not well versed. Can they explain further? Because I mean, if we're looking at the lighting design, we're looking at the efficiency of it. We're looking at the lumen output. We're looking at the photometric design of it, which is done in a programming that obviously will yield a better efficiency by using low voltages, but also getting higher lumen outputs in our designs. And then secondly, obviously, you want to do energy efficiency on even the supply cables and looking at the housing itself, what requirements will be needed in terms of the power supply, and how can they obviously do savings around that, which is a methodology which you will submit to a client for them to assist them in terms of future basically saving consumption.
Okay, and then there are quite a few comments and or questions popping up regarding why in the process solar wasn't considered, if you want to make a comment on that.
Okay, with solar PV designs, I've done quite a lot of them. There's a huge disadvantage when it comes to solar designs. It is your solar panels. Now, the first question you need to ask yourself is that if I'm doing a solar PV design, where will I be putting these solar panels? And in a certain project like this, they've utilized the roof space for solar panels for the main campus itself, and it's a grid-tied system. And therefore, here we've got sports field, which are always being utilized. Therefore, there was no area for solar panels. If you're looking at one solar panel, you're looking at a 2 meter by 1 meter solar panel. And that 2 meter by 1 meter solar panel, depending on which supply you get in, you're getting 500 watt of power for each solar panel. Now multiply that to try and get a loading of 125 amps, you're going to need quite a lot of space. I can even show you the calculations of the area you require, and TWC doesn't have that. And they didn't opt for that because they already have a standby generator, which they consider much more reliable for what is required on the student housing side.
Thank you. And then just for clarification, there is a question regarding the decision to go from an overhead power supply, that's the municipal along Villiers Drive, to an underground one. Why was that done? If you can maybe just clarify whether it was because of the positioning of the overhead structure and would have conflicted with the cables or not?
That is correct. That is correct. So while we are still at concept design stage, there was an existing overhead line. It was a 3-phase overhead line, an aerial bundle, which obviously was supplying the streets on the main campus side. So that overhead line would obviously cross or obviously, disturb the bridge where it needs to be stopped, because you've got 11 meter poles which are holding this ABC bundle, and therefore we needed the bridge to cross there. The same goes for the telecom as well. On the other side, they've got 9 meter poles with fiber lines. Those are obviously going to be clashing with the bridge itself. So therefore, the first thing that had to be done was to log applications with Msunduzi, who's the supply authority, give them drawings, mark off where exactly we need the conversion to happen. And therefore, once you've logged the application, they will do their own internal design because they are their supply authority and they will prefer to do things their way. And then obviously we just pay a relocation fee for that. So that had to be done based on that. It will clash definitely with the bridge once it starts being constructed. Same goes with the telecom as well. An application was logged and drawings were provided. We met with the technicians on site for both Msunduzi and Telkom. We decided on the scope, agreed, and then obviously they've converted that to underground system to allow wayly for the pedestrian bridge.
Right. I think from a time perspective, there's probably a few more questions in the chat. We'll circle back if we can. Thank you very much, Mdeni. And I think you're about to hand back to Pierre so we can see some of all this technical stuff in pictures.
All right. Thank you.
Lovely.
Thank you, everyone.
Thank you very much. Well done.
Okay.
Okay, just loading my one. Thanks, Mdeni. And
you're good to go, Pierre. It's loading. Here we are. You're good
great.
to go.
Okay, so we are a bit pushed for time, so I'll go through the initial slides quicker because they are more straightforward. But because I do have 2 videos that I'd like to share at the end. So this is just one of the footings for the piers. You can see how big that footing is, and you can see how red the clay material is, necessitating a decent sized footing. And on the other side, this footing needed an undercut, and we filled in the particularly bad material with rock fill to give it a more stable foundation. This is just the blinding, so that's that initial concrete layer. It's a low strength concrete 15 MPa. It's just to help you get off the ground and then put your steel work on top of it, and your shuttering and so on. So we always are relieved to get off the ground because then it's less affected by weather and that kind of thing, and we can build the proper foundation from there. So this is the beginnings of the steel work for the foundation, and there are just various things to look out for when on site. You've got to make sure your shutter is properly braced. This is normally well, it worked, but this was some of the bracing on the side because the concrete's very heavy, and when you put in a poker vibrator to make sure you take the voids out, your shutters, if they're not properly braced, they can bow out. And you need shutter release oil on the sides so you can peel your shutters off without damaging the concrete. You've got to check for cleanliness, your bar sizes and spacing. You've got to check that it conforms with the design. You've got stirrups here. These are things to separate the top layer of steel from the bottom. You've got spacer blocks. This is just looking at it zoomed up closer. That's your stirrup. And then your spacer blocks, those plastic things that get cast into the concrete to make sure that your steel is not right up against the surface, but that you've got your 30 mils cover for reinforcing, which protects the steel from rusting and keeps it well within the concrete. The concrete is protecting the steel. Then you've got your starter bars. So these are the starter bars for the main pier. You've got to make sure that they get cast into the foundation so that your pier is monolithic. It's one with the foundation. And likewise, this is the starter bars for the staircase pier, the back. And okay, we haven't shown the ducts in here, but the ducts were installed before the concrete was poured so that Mdeni could get his electrical services pulled through. And this is the poured version. and you can see that the ducts are sticking out of the foundation, so we didn't forget about that. And these are the starter bars, and they get for the two piers, the main pier and then the staircase support. And you've got to make sure that you vibrate your concrete properly to get all the voids out, partly for aesthetics, but mainly to protect your steel from moisture and air, and chemicals like chlorides that corrode the steel. So now we're getting further off the ground. We've got the steel for the two piers, and you need a certain overlap with your starter bars and the new steel that's coming up. And we've got circular shutters bolted together. And this is the first lift, the first pour for the two piers. This looks like it's a mistake, but it's not. I'll get to it now. But the important thing is that you can't pour this too high unless you've got a special kind of concrete. This was, I don't know, 2.5 meters looks like. You don't want to pour your whole column all at once, because then you get segregation. You get the coarse material separating from the fines. You get a compromised product. So that's why we tend to go in up to a certain limit in height. This here, you've got a close up here. These are, this is covering for the steel that's going to be peeled out of the structure to form a beam, a horizontal beam, which will provide support for the staircase. So there's one here, there's one over here, and they go in a spiral around the structure. And this is the next pour. And now you can see that those steel bars have been peeled out of the structure. And it's resulted in voids here, but that will obviously be filled in. That's on purpose. And so now you've got, look, here's more of a close-up. So those horizontal bars were actually inside the structure, and we peeled it out, and it's continuous with what's in the column, so that the beam is monolithic with the column. And here's the next lift, which has got the support for the deck, and these bars that are sticking up will be folded over horizontal to connect these two piers. Now, just something, this is not like the contractor ran out of concrete when he was pouring this beam. There's meant to be steel protruding from it, because this is where the stairs are going to go, and the stairs need to be joined with the beam. And for those new to reinforced concrete design and construction, the steel is what provides your tensile strength in the structure. That's why the main reason why we have the reinforced steel inside of the concrete. The concrete is strong in compression. The steel is strong in both compression and in tension. And so that's why the steel is so important. Now, this looks like it's a mistake, but it's not. This is the shuttering now coming in for the spiral staircase, and it doesn't look right. It looks like it's sagging in the middle. This is you're supposed to be able to draw a straight line from this corner straight through to the pier behind it, but you can see it sagging. This is where we come to the most difficult part of the project from a construction point of view. It's not the structural steel, it's not the deck, it's the spiral staircase, the concrete reinforced spiral staircase. And the challenge here is that this steel shutter needs to bend in two directions. But how do you bend steel, a thick steel plate, in two directions? So that's why it looks like it's got a straight line there, because you can't it's only bending in one direction. So in theory, you can get it perfect by maybe having a whole lot of small plates welded together that are wider on this end and then thinner on this end, and making it go up like a spiral. Or maybe in future, people will use 3D printing of their shutters if that becomes viable. But what the contractor came up with quite a clever idea of how to get this right. And that is the sagging of the underlying shutter. He just filled it with a weak concrete. And then he put a black bond breaker on top of it. He painted a bond breaker similar to shutter release oil on the sides. And so this was later going, all this concrete here that you see is going to get chipped off eventually, and has been. So now you've got a flat base for your real concrete. And these are the starter bars coming out of your beam that will get bent to follow the profile of this underneath the stairs. And your stairs will come on top of that. Okay. So here you've got the shuttering now for the staircase, that the risers of the stairs is where those wooden, the backs of those wooden planks are. There's no steel in the actual stairs. The steel is underneath the stairs. And in the background, what you see there is concrete, that weak mortar that has been painted with a black bond breaker so that you can take it off. You can actually remove that existing concrete. And this is about to be poured. You've got the steel reinforcing to support the stairs. In order to get the concrete up to the right height, as Jimmy said, it's around 5 meters, you've got to get it, was poured into this loader. This loader's got a telescopic arm that can extend higher. And so there you've got the vibrating to get the voids out, and you've got the finishing off. We left a fairly rough finish, almost like a wood float, so that the steps are not slippery. Now, the finished product. I'm not serious. Okay. This is the underside of the staircase, but this is that weak concrete we were talking about that needs to be chipped out, removed. So here's a guy grinding off the weak concrete and getting it ready. So it's starting to take shape. And then this is the finished product. So it's amazing what Photoshop can do. I'm joking. That is what it's looking like. And we can now move on to the launch of the steel deck. We've got 2 videos. The launch of the steel deck, and then I will do a walkthrough with commentary of the finished product. So sit back and enjoy, and then we can finish with some.
Don't forget to select the sound, Pierre.
Correct. This first video is courtesy of the Wykeham Collegiate.
No sound, Pierre. You forgot to click the share sound.
Got the sound. Okay, I'm not sure why that happened. I'm going to close that app and reopen it. Hear it now.
No, I think it's your share screen. When you're sharing screen, you must click that use computer sound button, or else we won't hear the sound, Pierre. So it's not what you are streaming. You are hearing it, I'm assuming, but we can't.
Yeah, when you share screen, you've got to
Right at the top of share, just to include sound, and then it should work fine.
Yes, I did enable that. I will, but it did work with the mic unmuted. I'm going to try share screen with including sound. See if that helps, rather than share window. Can you hear it?
No, no sound.
Okay, this is fine because this is just music. On the next one, it's got commentary.
Okay, maybe you can just talk us through what we are seeing. Pierre, if you don't mind.
Yeah, so the next video has actually got a lot of commentary that covers a lot of what we see here, but you can see it's all being launched as one deck. Okay, now it's going back to where it's about to be launched. You can see there's shutters for the deck that will then be, the concrete will be cast on top of that. So this happened on a quiet Sunday afternoon. It's now coming in place. And then they're going to bolt it down on the one side, on the one corner, and make sure it's properly aligned on both ends. So this was about 2 months ago. They had just finished welding the 3 sections of the deck together because the deck was made in 3 sections, 3 more or less equal sections. Might be okay.
Yeah, you may have hit the pause button, so just check you haven't paused the video.
Okay, I see on your side it's frozen. Okay, it's finished. There wasn't a lot more to see from that video. I also see that it's frozen there. I'm not sure why.
Okay, let's jump to the other one, and hopefully that one will give us both sound and run through to its logical conclusion.
Otherwise, I can do a running commentary.
Cool. Yeah, I think we've lost you as well now. Okay, just be patient, folks. I think they're just re-logging in with Jimmy's laptop again, or changing over to Piers. It's called technological challenges, more so trying to present what they did than the actual structure itself.
Okay, sorry about that. Can you all hear me?
We
Sorry,
can
can
hear
you all
you
hear
now,
me now?
Pierre. Sorry, I was just phoning you to say we lost you, Jimmy. We don't have a connection to Jimmy, but we can hear you. Pierre, can you hear me?
I can't hear Tom.
I can hear you, Pierre.
Tom, I can't hear you. Let's try join on that one. Sheesh. Okay, I'm also Can you hear me?
Yeah, we can hear you, Pierre. It's just you that apparently can't hear me, but everybody can hear me and hear you. So
I think it's running through the TV. That's probably why you can't hear it. The volume's up on the TV, maybe.
Okay.
Try now.
Pierre, can you hear us now?
No.
Yeah, we can hear you, Pierre. When all else fails, go to the chat.
Okay, I can hear you now.
Okay,
Sorry.
and we've been hearing you since the word go. So you are loud and clear. Are you going to try and run that video from your laptop now? The second one. Okay, cool.
Yeah.
Go for it when you're ready.
Sorry about that.
No problem.
Okay, I'm going to share it now. I've loaded it up.
Great. You did select share computer sound as well.
I'm going to do that now. Yeah, you know, we tested it with you.
Yeah, well, those that
Murphy's
joined
Law.
early had the live and the sound, so we've given them a sneak preview, but we'll get it right. Patience is a virtue. I was telling the delegates in the session when you were offline that that sharing the video has been more complicated than building the whole bridge. Coming up now, Pierre, while we can see your Outlook, your Explorer.
Right, so it's late October and we're almost done. And
almost
almost ready to hand this bridge over.
We can hear perfectly, Pierre.
Over here you can see there's some permanent shutters in place. Those were there when the deck was being launched. They were already installing them onto the steel members. And then after that we cast a concrete footway on top of those. Here's your spiral staircase, or the mathematical purists would say it's a helical staircase. You can see we're still doing some cleaning up. Over here on the side you can see that the outer balustrade is bolted on the side, and those are chemical anchors, chemical bolts. So we drilled into the side and epoxied the threads in place. The other common alternative is to use mechanical bolts or expansion bolts. You know, they expand as you tighten them up. We prefer chemical bolts, and the main reason is that with expansion bolts you're putting an initial stress on the concrete when you're tightening it up, even before you've actually stressed the balustrades. Those are hot dipped galvanized balustrades, and then on top of that you've got your stainless steel handrails. Okay, so obviously there's still some masking tape here because they're busy painting the balustrades. Now underneath this we applied a primer coat, a dark grey coat that enables the final coat of paint to bond with the galvanized steel. Okay, so you can obviously see that on the inside the tread is narrower than on the outside, as one would expect with a spiral staircase. Now on the inside we had a bit of a challenge because we couldn't get the drill between this member and the interface. So we opted to drill a core on the top and insert it vertically into the core. Here's an example of our lights, and you can see more clearly the permanent shutters on which the concrete was later cast. Okay, so here's our deck. You may be wondering why we have this diagonal member here, and on this side, on all four corners. Well, a triangle is a lot stronger structurally than a square or a rectangle. So with that diagonal member in place, it gives stability in this direction to this overall section. Okay, this cross bracing is to stop movement in this direction between these two sides. Now the deck is anchored to the abutment underneath the concrete here with 4 bolts. So in this corner it's totally fixed. Whereas on this corner you need to allow for some differential movement between the deck and the underlying abutment. So we've put in a bearing that allows movement in that direction. Here's your bridge joint, which also allows movement in expansion and contraction and sideways movement. Over here, you might be wondering what that is. That is your earthing for your lighting protection. So we did a soil resistivity test and made sure that our lighting protection was adequate. So that connects down into the ground. You might be wondering why there are holes over here. It's not for drainage, I can assure you. Basically, all these members are galvanized steel. So they're hot dip galvanized. They put in a 450°C zinc bath, and what happens then is that the zinc bonds with the steel. It's actually not a separate layer. It's not like it's painted on. It's actually bonded properly into the steel, and what happens is that zinc gives cathodic protection to the steel, and so it's basically the zinc that rusts rather than the steel. And when zinc rusts, it just goes a slightly duller color. It doesn't expand and look unsightly. So and it preserves the underlying steel, and so the structure retains its strength. But coming back to the issue of the holes, you can imagine these are hollow sections. You can imagine how hot the air gets inside there when you put it in a 450°C bath, and then all of a sudden it expands. You need to get the air out of there as quickly as possible. That's why you've even got holes in the top as well. Otherwise the whole thing will explode and it'll be catastrophic. Over here you can see the LED lights that run along the entire length of the top on both sides. Now this deck was assembled in 3 sections, 3 equal sections. So there are 3/3 to this deck, and it was galvanized in thirds, because you can imagine putting this whole deck into a zinc bath. It's not going to fit. And also, how are you going to transport the whole thing? So what you do is you weld up a whole section, a whole third of a deck, and then you galvanize it, because you don't want to damage the galvanizing with unnecessary welding. And another beauty of hot dip galvanizing is that it obviously coats the inside and the outside. of the hollow sections. Then we welded over there and over here, and so we joined up the sections in this way. We welded it after the galvanizing, so of course the galvanizing is slightly damaged there, but we obviously just have to keep it painted and touched up. And so that was welded on site before the assembly, and then the whole thing was the whole deck was lifted and put in place. These boxes are to do with the lighting. Now over here, this is where the cables for the electrical ducts were put in place on the underlying pier here. So there are some 110 millimeter diameter ducts and some 50 millimeter ducts that were cast into the pier at the time that it was cast, to allow for people to pull cables through, because and then they came up through the concrete and through this member here, and you can see them coming out there and feeding the lights. And also there's the process of installing CCTV on this deck, so to monitor comings and goings. So that also needed ducts. Okay, so that's our bridge.
Right, Pierre and team, that's fantastic. Pierre, can I just check if you've seen, do you know if any representative of the client is in the session? Anybody from TW, I mean, besides interested parents and other parties, but is Charles from the client? There's a hand. I don't know if he's volunteering that he's from the client or waving goodbye, one of the two.
I don't see a name that I recognize, but I haven't, I've only looked at a small fraction of the names. But I know that there are TWC families involved. I'm just not sure if they are direct project role players involved, those who had direct input into the project.
Okay. No, I just wanted to at least acknowledge the client. So in the absence of maybe the body corporate or governing body, as they call it at TWC, being present, I think good foresight from the school, not only to consider such a civil infrastructure intervention to get the girls safely across the road from one side to the other side, but also to be investing in local, both in terms of consulting. What you did not tell the delegates, that your office is the site office, because if you look out the window of your boardroom, you look straight onto the site. So I don't think Jimmy needed to walk too far to check that the piers were going up in the right place, and likewise with yourself and Mdeni. So from SAICE's perspective, well done TWC for investing in both the Pietermaritzburg economy and the sightline. I heard the Airlink flight coming in over your head while you were filming their pier. I'm not sure if that was the midday flight or the late afternoon flight, but it's on the flight path. So I'm sure when passengers fly into Maritzburg in future, one of the things they'll see is not only the Astro tennis courts and swimming pool of TWC, but they'll also have a good sight of your pedestrian bridge, particularly the late evening flight when it's nicely illuminated. And if I remember correctly, you said the official opening is coming up on Monday next week, is it? The 4th of November?
Correct.
And I presume Jimmy's loading is going to be tested by the entire school, trying to see if they can fit on the bridge. No, I'm teasing you, Jimmy. Can I just check, is there anybody else that would like to have a quick engagement with the team? There are still questions in the chat, but the chat is enabled. Charles, I'm going to enable you so you can go ahead.
Just before Charles speaks, if you don't get a chance to ask, just a reminder, my email address is pierre, PIERRE, @HN Hotel November.co.za. Charles.
Charles,
Good evening, and thank you so much for a good presentation. Great work done there, Jimmy and team. I'm a structural engineer myself. It's amazing to see such projects going on in our country. Just one question. I see you don't have any bottom bracing. Did you leave them for any particular reason? Because you've got your concrete deck, but you don't have any bracing at the bottom.
Yeah, look, the deck is concrete, so it's pretty stiff naturally, but there is actually bracing there. There are horizontal braces going across that kept it in position while we lifted it.
All right, thank you.
Yeah.
Right, so just a reminder, it's Pierre with a double R @hn.co.za, and if you'd rather talk to Jimmy, it's Jimmy at the same, I think it is, if I remember correctly, and likewise with Mdeni. Again, the chat is open, so keep an eye on the chat if you want to have further comments, and I'm pretty sure once Pierre, Jimmy and the team have regrouped and got their sanity back from their evening stresses and strains, they will perhaps attend to some of the questions that were unanswered.